If you ever stand on a dock next to a modern commercial cargo ship, the first thing that really hits you is the sheer, uh, incomprehensible scale of the thing.
Oh, absolutely. It's massive.
Right. It is like looking at a skyscraper that someone just decided to lay on its side and float on the water. And when you look down at the main deck of that ship, it looks like this massive, flat, uninterrupted expanse of steel.
Yeah, it looks like a giant metal parking lot.
Exactly. But that is actually an illusion because, that deck isn't a solid floor at all. It is mostly a series of giant heavy-duty lids.
Yeah, and if you strip away those massive steel lids, a cargo ship is fundamentally just an open bathtub floating in the middle of a very angry ocean.
Which is a terrifying thought, honestly.
It really is. And that ocean is constantly trying to get inside. So today we are focusing our deep dive entirely on the engineering marvels that keep the water out.
Right, and we have a very specific mission today. We are unpacking Chapter 9 of a technical maritime manual on hatch cover construction. And our goal is to explain these mechanisms simply, specifically tailoring this for beginner trainees stepping into the maritime world.
Yeah, because if you're a trainee or honestly, even just someone fascinated by massive industrial machinery, understanding how a ship moves thousands of tons of steel just to open and close its own deck is absolutely foundational.
Without these closures, a cargo ship simply cannot survive at sea. So, okay, let's unpack this.
Let's do it.
We are talking about hatch covers. But a hatch cover isn't just, a basic lid to keep the rain out, like the lid on a plastic storage bin.
No, not at all. These are incredibly complex structures engineered with a crucial dual purpose. First, obviously, they have to create a flawless, watertight seal over the cargo hold.
Right, to prevent the ingress of seawater.
Exactly. But second, they have to act as the primary supporting structure for deck cargo. So it isn't just a roof. It has to be a floor strong enough to stack hundreds of tons of extra shipping containers on top of.
Which introduces a massive engineering contradiction right out of the gate. I mean, to support hundreds of tons of cargo, these covers must be constructed from incredibly thick, heavily reinforced steel grating and plating, right?
Yeah, they are essentially horizontal steel walls.
But because they're made of all that reinforced steel, they're exceptionally heavy. Yet they still need to be moved efficiently every single time a ship needs to load or unload.
That's the real challenge. You have a mechanism that needs to be as impenetrable as a bank vault, but as easy to open as a kitchen cabinet.
And seeing how engineers have solved that contradiction over the decades is what we are exploring today. We are going to walk through the 4 primary mechanical solutions used across the global shipping industry.
Right, the 4 different ways to move these unbelievable amounts of steel.
Yeah. And to really grasp how these work for our trains out there, we shouldn't just list them. We need to look at the evolving operational challenges ships actually face.
That makes sense. Context is everything.
So let's start with the scenario of a massive, modern container ship pulling into a high-tech, deeply developed megaport, places like Rotterdam or Shanghai.
Oh, right. That environment relies heavily on our first category, the lift-away or lifting type hatch cover.
So how does this one work?
Well, this is a system built entirely around the concept of modularity. Instead of engineering one gargantuan lid to cover a massive hatchway, the opening is covered by a multi-panel unit.
Got it. So you have several separate, independent steel panels sitting side by side over a single hold.
Exactly.
The easiest way to visualize this, I think, is to think of a giant Lego baseboard. Imagine you've snapped down a row of flat, rectangular Lego plates over a hollow space.
That's a perfect analogy, yeah.
When you want to get something out of that space, you don't have to rip off the entire roof all at once. You just reach down and pull up one specific Lego plate right in the middle, leaving the rest perfectly in place.
And what's fascinating here is the strategic value of that exact mechanism. That independent, partial opening provides a massive operational advantage, particularly when dealing with weather constraints.
Wait, how so? Because of the rain?
Yeah, imagine you are in a port and a sudden squall rolls in, or the sea spray is particularly heavy. You only need to unload a specific stack of containers from, say, the forward left section of the hold.
Oh, I see.
With a lifting type cover, the crew removes just that one specific panel. They access exactly what they need, while the rest of the highly valuable cargo in that hold remains completely protected from the elements.
That is brilliant. It brings surgical precision to what is otherwise a totally brute force operation.
Yeah.
You are actively minimizing your exposure to the environment.
Precisely. And because these are primarily used on container ships, the way they are moved is deeply integrated with the way containers themselves are moved.
Right, because you can't just flip these steel plates open with a crowbar.
Definitely not. They are lifted using a specialized piece of equipment called a spreader. And that spreader is usually attached to those massive, towering gantry cranes you see lined up on the shore at major ports.
So the spreader is essentially a heavy-duty rectangular steel frame.
Yeah, the crane operator lowers it down from the sky, and it physically locks onto the four extreme corners of the steel hatch panel.
And it uses the exact same locking mechanism called twist locks that it uses to pick up standard shipping containers, right?
Exactly. It's completely integrated. Once it locks in, the crane hoists the entire steel panel straight up into the air, completely separating it from the ship.
It's basically an industrial claw machine. It drops down, grabs the steel plate, lifts it vertically, and moves it entirely out of the way.
Yeah, and usually it just stacks that panel on another part of the deck or sometimes right onto the concrete dock next to the ship. It's a very elegant, clean solution.
Elegant, provided you have the infrastructure. And I guess that is the critical limitation of the lift-away system. It relies almost entirely on external vertical lifting power.
Exactly. If you are sitting under a 200-foot tall shore crane, lifting type covers are incredibly efficient. You just pluck them off. But a ship isn't truly independent if it cannot open its own hatches.
Exactly, which transitions us perfectly to the next engineering hurdle for our trainees. What happens when a ship leaves those high-tech megaports?
Right, because not every port has a skyline filled with massive gantry cranes.
Exactly. Imagine a general cargo ship carrying a mix of steel coils, bags of grain, maybe some heavy machinery. The ship has to rely on its own built-in muscle without swinging massive steel plates freely through the air.
And that requires a totally different mechanical approach. This brings us to the folding type hatch cover.
Okay, so how does the folding type work?
This is where we shift from vertical lifting to mechanical leverage. The fundamental design of a folding cover consists of two flat-topped steel panels that meet in the middle over the matchway. When it is time to open them, they push upward and hinge in the center, folding into a peaked tent-like shape. Then, as the mechanism continues to push, the two halves fold entirely together and stow upright at the very edge of the hatch.
If you want a visual for this, think about the folding attic stairs in a house or a massive set of cellar trap doors. You push up from the center, the hinge pivots, and the two halves fold against each other.
That's a great way to picture it.
But here is where I have to push back a bit on behalf of anyone trying to wrap their head around this. If we are talking about a vessel that is hundreds of feet long, and these panels are made of incredibly thick reinforced steel.
Which they are, yeah.
How on earth does a crew actually lift them? I mean, trying to push up a wooden attic door is hard enough. A steel panel that size must weigh tens of thousands of pounds. Pushing it straight up into the air seems like a battle against gravity that human beings just can't win.
Oh, it is a battle human beings can't win. You couldn't even do it with a complex system of ropes and pulleys. The sheer physics involved require raw, concentrated power.
So what's the secret?
Because these covers have such massive dimensions and extreme weight, they absolutely require heavy-duty hydraulic rams to force them open.
Right, we're talking about hydraulics.
Right.
The mechanical power of pressurized fluid.
Exactly. When you look closely at the hinges and the outer edges of these folding covers, you will see massive steel cylinders. Inside those cylinders is a piston.
Okay.
When the crew activates the system, a high-pressure pump forces incompressible hydraulic fluid into the cylinder. Because the fluid cannot be squashed, it has nowhere to go but against the piston, forcing it outward with immense pressure.
So a relatively small fluid pump generates thousands of pounds of force.
Precisely. That hydraulic ram is the physical muscle that forces the heavy steel panel upward. It fights gravity head-on, raising the steel up into that tent shape and then aggressively pushing it back into its stowed vertical position.
It is a brilliant application of fluid dynamics, overcoming the immense static weight of the steel.
It really is.
So the ship essentially has these massive hydraulic muscles built permanently into the deck. Now, there is a really interesting spatial detail regarding these folding covers that trainees should know.
Oh, about the tween decks.
Yes. Obviously, they are fitted on the weather deck, the top exposed deck that takes the brunt of the ocean storms. But they can also be utilized deep inside the ship on something called the tween deck.
Right, and for anyone new to the terminology, tween deck is simply an abbreviation for between deck. Large general cargo ships aren't just one giant hollow cavern on the inside.
They have levels, right?
Exactly. If you were to walk down into the hold, you would see intermediate floors, or shelves, built horizontally inside the ship. These exist to separate different types of cargo so they don't crush each other under their own weight.
That makes perfect sense. If you have heavy steel parts, you don't want them sitting directly on top of, fragile pallets of electronics.
Exactly. So you have a watertight hatch cover on the roof of the ship, but you also have these folding hatch covers acting as trapdoors on the floors down inside the belly of the ship itself.
And the beauty of the hydraulic folding mechanism is that it is self-contained. It is compact enough to work down in those enclosed lower levels where you have absolutely no overhead clearance for a crane.
Right, you just activate the hydraulics, the floor folds up into a tent, and you can lower cargo deeper into the ship.
But let's look at the physics of what we've covered so far. Both the lifting type and the folding type require an immense amount of energy.
Oh, totally.
Lifting them with a crane requires massive electrical output. Folding them with hydraulics requires high-pressure pumps constantly fighting the downward pull of gravity. If I'm an engineer trying to save mechanical energy, I don't want to fight gravity at all. Is there a way to bypass vertical lifting entirely?
That is the exact question that led to our third category, the rolling or sliding type hatch covers.
Here is where it gets really interesting. Instead of lifting up like Lego pieces or folding up like a heavy steel tent, these systems consist of solid steel covers that simply slide out of the way on wheels.
Yeah, they just roll.
If the folding covers are like an attic door, these are like massive sliding barn doors or those heavy sliding glass doors on a patio. You unlatch them and they glide perfectly flat along a horizontal track.
And if we connect this to the bigger picture, the reason this design dominates on certain types of massive vessels like bulk carriers hauling coal or iron ore is purely about mechanical efficiency.
Right.
By keeping the massive steel panels perfectly horizontal and putting that incredible weight on precision wheels, you shift entirely from vertical lifting to horizontal rolling.
The efficiency of the wheel, it's one of humanity's oldest inventions, still doing the heavy lifting on the most advanced ships.
It really is that simple at its core. You don't need a towering overhead crane. You don't need highly complex, high-pressure hydraulic rams straining against gravity.
You just need a relatively simple electric or hydraulic motor to pull the panel along a flat track.
Yeah.
It requires a fraction of the energy to roll heavy steel horizontally than it does to push it vertically.
Absolutely. And the terminology used to describe how these roll is important for trainees to grasp. Depending on the design of the ship, these panels can slide sideways across the width of the ship, which in maritime terms is called rolling a thwartship.
The thwartship, okay.
Or they can slide lengthwise down the long axis of the ship toward the bow or the stern, which is called rolling longitudinally.
But wait, this brings up a massive engineering conflict. A sliding door on wheels is inherently loose. It has to be loose, with a gap between the door and the floor in order for the wheels to skin freely.
That's true.
But the very first thing we established today is that the primary mission of a hatch cover is absolute watertight integrity. If this massive steel door is hovering on wheels, how does it seal out the ocean?
That is the brilliant part of the design, and it relies on a component called the cleat. When that massive panel rolls on its rails into the closed position, it isn't actually watertight yet.
Right, because it's still on the wheels.
Exactly, it is just sitting there on its wheel boxes. But around the perimeter of the hatchway is a thick, heavy-duty rubber gasket. To create a seal, that rubber has to be aggressively crushed against the steel lip of the hatchway.
So the wheels get it into position, but something else has to lock it down.
Precisely. The cleats are heavy-duty mechanical clamps spaced all around the edge of the cover. Once the cover is rolled into place, the crew, or an automated hydraulic system, engages the cleats.
Okay, and what do they do?
These clamps physically grab the edge of the steel panel and forcefully pull the entire structure down. They pull it off its wheels and smash it down into that rubber gasket.
Oh, wow.
Yeah, the cleats transition the cover from a freely moving vehicle on wheels into a locked, sealed, impenetrable vault door.
That is an incredible visual. The whole heavy roof actually drops down into the rubber to seal the ship. But as brilliant as the rolling system is, I see a glaring physical limitation. Sliding massive steel panels perfectly flat across the deck requires a lot of empty dev space to slide them into. If you have a side-rolling cover moving a thwartship, it means when the hatch is open, the cover is hanging out over the left and right sides of the hatchway.
Yes, exactly.
On a ship where every square foot of deck space equals potential profit, Why sacrifice that real estate?
You've hit on the exact trade-off. Rolling covers demand an enormous deck footprint. On a massive bulk carrier in the open ocean, you might have that extra width to spare. But what happens when you are operating in highly constrained environments?
Right. What if you aren't on an ocean-going behemoth? What if you were on a smaller vessel, like a river barge, navigating tight inland waterways?
The space just isn't there.
The deck space is highly limited, the hatch opening takes up almost the entire width of the boat, and you definitely don't have massive shore cranes or room for sliding barn doors.
Necessity breeds invention. And those exact spatial constraints give us the fourth and final mechanical solution, the roll stowing type.
I look at these as the ultimate space savers. The mechanism here is completely different from the solid, massive panels we've been talking about. Instead of two giant plates covering the hold, a roll stowing system uses a long series of much smaller, segmented covers.
It's really a masterclass in maximizing limited geometry.
The best analogy for this is deck of cards. Imagine you have a deck of cards laid out end-to-end across a table. When you want to clear the table, you don't sweep them off the side. You push them all together, gathering them up and stacking them neatly at one end into a tight, compact deck.
Yeah, or think of how window blinds work.
Oh, right. When you pull the cord, all those individual horizontal slats gather up and stack tightly together at the top of the window, getting completely out of the way.
That perfectly illustrates the motion. But instead of a simple pull cord, these barges use a highly specialized piece of equipment. Built directly into the end of the hatchway is a mini hydraulically powered lifting crane facility. It is a dedicated, automated stacker.
So the barge carries its own personal robotic arm just for the covers.
Yes. When it's time to open the hatch, this automated system physically lifts the first small steel segment, rolls it back, and then lifts the next one.
Just one by one.
Exactly. It continuously gathers them, lifting and stacking them tightly together, one on top of the other at the far end of the hatchway. It creates a neat vertical stack of steel panels.
And by stacking them vertically at one end, you clear the entire length of the hatchway for loading cargo. You don't need the massive empty side deck space that a sliding cover requires, and you avoid the immense hydraulic power required to fold a massive solid panel into a tent against gravity.
Right, you just neatly file them away at the end of the boat. It is tailored completely to the constraints of a barge.
It is an elegant, compact solution to a very specific spatial problem, proving that maritime engineering is always about adapting the machine to the environment it operates in.
Absolutely.
So what does this all mean? If you are a trainee or just someone listening who wants to understand how the modern world actually works, let's summarize the engineering journey we've just taken.
Let's recap.
We started with the realization that a ship's flat deck is actually an armored lid designed to seal the bathtub while simultaneously supporting hundreds of tons of cargo. And we've explored the 4 ingenious ways engineers manipulate that massive weight.
First, we have lifting covers.
Right, relying on external gantry cranes to plug panels away like surgical Lego pieces. Then we have folding covers, relying on the fluid mechanics of built-in hydraulic rams to fight gravity and push the steel up into a tent shape.
And then the rollers.
Yes, rolling covers, utilizing the ancient efficiency of the wheel to glide massive weight horizontally before heavy-duty cleats crush them down into a watertight seal. And finally, we have the roll stowing covers, using dedicated mini cranes to tightly stack segmented panels like a deck of cards to save space on narrow barges.
Understanding these mechanisms completely changes how you see the industry. But before we finish, this raises an important question, something really fascinating for you to think about long after we wrap up today.
Ooh, what's that?
Well, we have spent this entire time talking about how incredibly rigid, massive, and heavy these steel structures are. We've talked about precision wheels rolling on perfectly straight rails, tight locking cleats, and heavy-duty steel hinges.
Right, completely solid.
But ships operate in a dynamic, violent environment. Imagine one of these massive cargo ships caught in a severe ocean storm. The ocean waves are not uniform. The bow of the ship might be riding up a massive swell while the stern is crashing down into a trough.
Which means the ship is bending.
Exactly. When that happens, the entire steel hull of that ship is physically twisting, torquing, and bending. It has to flex or it will snap. So here is the paradox to ponder. How do you think these perfectly rigid, heavy steel covers manage to flex along with the twisting hull of the ship without popping off their tracks, snapping their hinges, or breaking that perfect, life-saving, watertight seal?
Wow, that is a brilliant mechanical mystery to leave you with. A massive structure that must be entirely unyielding to water, yet flexible enough to survive the torsion of the open ocean.
It really is something to chew on.
Next time you see a cargo ship on the horizon, you won't just see a flat deck. You'll see a dynamic, heavy-duty mechanical puzzle, constantly working to keep the ocean out. Thank you for joining us. As we unpack the heavy machinery of the maritime world, we will catch you on the next deep dive.